Well, hello everybody, and we are going to go over some basic rules of differentiation in this video. And you already know about the power rule. We've kind of talked about that to some extent and practiced with it quite a bit already. So that one should be pretty easy to apply. And to go along with the power rule, we have something called the constant multiple rule and the combination rule. And I think you've sort of really been doing these already. So one thing about the constant multiple rule is that you can take a constant and it can come outside a calculus symbol. And if, and there's a little error here, this should be a u. If u is a differentiable function of x and c is a real number, then c times u is also differentiable, and the derivative is just going to be c times the derivative of u. Okay, so what does that sort of mean here? Well, if I've got a function like 4x squared, it's sort of like I can pull the 4 off to the side, then I can deal with the derivative of this thing next, and then put it all back together again at the end. Okay, but that's just an application of the power rule that I'm pretty sure you're comfortable with. And really what you're doing here is the combination rule if you do it all in one step. So if you have the derivative of some function with respect to x and it's c times x to the n power, then it's going to be n times c times x to the n minus 1. So take the same function here and just do the derivative. It ends up as 8x because you just do it all in one step. So again, this is not something that is really, earth-shattering by any means, but it is important to kind of know that it's there in case we need it for some different situations. All right, so let's kind of put these to work and take the derivative of these functions. Let's start with this one here on the left. And actually, before I do that, I would encourage you to pause the video and try these on your own and see what you do. So go ahead and pause the video and work all three, and then I'll come back with the answer here very shortly. All right, so now that you see the derivatives of each one of these functions, you can see that they were pretty easy to get. Just a quick run through here. I rewrote this as 2x to the 1/2 power for part A, and then 1/2 times 2 gets you just 1, lower the power by 1, and then just simplify from there. Now, one thing I want to point out is this notation right here. It's going to be very important that you have that in your answer so I know you are talking about the derivative. So whether you're using this dy over dx or y prime or f prime or g prime, whatever you're using, just make sure it's in your answer so we know what the derivative is. No one's going to know unless you tell us. Okay, so for this one, this is another one where it's kind of like rewrite, derive, and simplify. So because this is in the denominator, I went ahead and wrote it as a x to the negative 2/3. Then I multiplied by negative 2/3, dropped the power by 1 to make it negative 5/3, and then it becomes clean up on aisle 2, and then a simplification because we don't like negative exponents. And this one over here, e, I guess that was c, I couldn't see it there. E, you could just separate out this x, and then once you see that, the derivative drops super fast. It's just going to be negative 3/2. Okay. Here's another one that you just make a lot of common sense out of, and that's the sum and difference rules. And that is, if u and v are differentiable functions of x, then their sum and differences are differentiable at every point where u and v are differentiable. So at those points, you're just going to take, if it's the sum and difference of sum or difference of u plus or minus v, then the derivative is going to be the derivative with respect to x of u plus or minus the derivative with respect to x of v, sometimes known as u prime plus v prime. So when we did this back in an earlier lesson, I kind of alluded to this as doing this one term at a time. So this is sort of like our one term at a time rule for polynomial derivatives. And then we can extend that to any finite number of functions. So if big F is little f plus little g minus h, then its derivative is going to be little f prime of x plus little g prime of x minus little h prime of x. And that's, again, all this is really intuitive. So I don't want to spend too much time on this because I think you already know it and are comfortable with it. So for something like this, once again, I want you to go ahead and pause the video and attempt these three derivatives and see what you come up with. So hit pause and check your answers in a moment. All right, and here are the answers for these three. And again, you're just kind of taking it one term at a time in each case here with the sum and difference rule. So using the correct symbol, since this is f, I'm going to call it f prime. Since this is g, I'm going to call its derivative g prime. And since y is being expressed as a function of x, I'm going to use the dy over dx. You could alternatively use y prime here if you wish, but I kind of like the dy over dx typically. So that's a look at the sum and difference rule. Not bad. Slope. Okay, now here is an excellent question, and we are going to see quite a lot of this particular calculus task in our class, and that's the idea of finding horizontal tangents. So the question is, does the curve y is equal to x fourth minus 2x squared plus 2, does it have any horizontal tangents? And if so, at what values of x do they occur? And no peeking at the graph. No peeking allowed. Okay, well, lucky for us, calculus to the rescue. So time out. If a tangent is horizontal, what does that mean? Well, if any line is horizontal, then we know its slope must be 0. Okay? So if a line's slope is 0, then that means that the derivative is 0. Okay? So the strategy here is find the derivative and set equal to 0 and solve. Okay, so now that might kind of give us some algebra task to do in a moment. So let's go ahead and find the derivative first. dy over dx is going to be 4x to the third minus 4x, and then the 2 drops out. So now, in order to find where those horizontal tangents are, I'm going to go ahead and set this equal to 0. And I think we should probably factor this because even though it's a cubic, I think it'll drop pretty quick if we use algebra to solve this instead of trying to rely on other sources. So we're going to factor out a 4x, and that's going to leave x squared minus 1. And then, of course, that factors further into x plus 1 and x minus 1. And now this is fully factored, so we can solve this super fast, as we all know from our zero product property, because if something else times another something else is 0, then by gosh, one of these three things had better be 0 in order for that statement to be true. So either x is 0, x is -1, or x is 1. Those are the locations of the horizontal tangents. So we kind of going back to the idea, no peeking at the graph here. Now that you know this information, it's probably safe to say that there might be turning points at each one of those functions. Now, it's not guaranteed that there are turning points, but it might be turning points. So, good information to know. All right, now, folks, parentheses matter here, and so do the rules of exponents. So when we derive things, you want to make sure that you take care of all your grouping symbols and your parentheses first before you jump into other stuff. So let's go ahead and let's kind of make this work here. This first one on the left, you notice there are no parentheses. So that means that I could rewrite this as 5/2 x to the -3. And when I go to find its derivative, well, I'm going to multiply the coefficient by -3, so that's going to give me -15/2. And then I drop the power by 1, x to the -4th, and then simplify once again. So the only thing that's got a negative exponent is the only thing that crosses the line here. And that is going to be the x Everything else stays where it is. And that should be your answer right there. Okay, now in this case on the right, the difference is the parentheses and the position of the power. So we're going to go ahead and power this thing out first, is what we're going to do. And 2 cubed is 8, and x to the third is 3. So I can rewrite this as 5 over 8 x to the negative 3. And now I can differentiate it and get an answer here of negative 15 over 8 x to the negative fourth. And then I'm going to just get that simplified really quick the same way I did the other one. So you can see that those parentheses make a big difference. And try it for yourself here. Try it for yourself, pause the video, try these two and see what you come up with. All right, and the second one a little frightening here, but the first one not so bad. The only thing that's got a negative power is the x. So I move it up to so-called ground level and separate out the constant here of 7/3. And differentiating it, not too bad. It's going to drop real fast using the power rule. Now over here, this entire set of parentheses, that's what had the power on it. So I'm going to move that entire set up to ground level. Then I'm going to apply the exponent to each of the things that's inside the parentheses. I'm going to go ahead and multiply in the 7. And now it seems like I'm in a position where differentiating isn't going to be too bad. So I'm going to end up with 126x. Okay, that's a good start here on some of the basic rules of derivatives, and we'll see you down the road. Good luck.